From Chicago, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
Our group is responsible for component development of liquid rocket engines. So that entire life cycle from the conceptual design through the manufacturing, and then ultimately the hot fire testing, which is really the exciting part, and I think why a lot of us got into the business.
That was Paul Gradl. Paul is a senior propulsion engineer in the Combustion Devices Design and Development branch at the NASA Marshall Space Flight Center. He leads the manufacturing, design, development, and testing of nozzles and nozzle extensions. For over a decade, he has supported a variety of nozzle development and flight programs and has been involved in technology development, supporting the manufacturing and measurement techniques for nozzles. Paul joins the show today to discuss his work to develop additive manufacturing for combustion devices for rockets. He also shares some sweet videos that you can check out in the About section of the podcast or on our website, www.3degreescompany.com. Thanks for joining the show today, Paul. For kind of getting started with the conversation, you're a senior propulsion engineer at NASA. Can you tell kind of the audience or the layperson, like, what does that mean? It sounds awesome. I want to learn more.
Sure. Yeah. So appreciate you having me on and look forward to a fun discussion on this. So the role that I work at NASA Marshall Space Flight Center, our group is responsible for component development of liquid rocket engines. So that entire life cycle from the conceptual design through the manufacturing, and then ultimately the hot fire testing, which is really the exciting part, and I think why a lot of us got into the business. So as part of that, we're responsible for leading a lot of multidisciplinary teams, which can be thermal, structural, fluids, mechanical design, and the manufacturing side of it, working with a lot of the test area engineers and technicians for setting up our test programs. So we really get to see that entire life cycle of the component development. We also work a lot of flight programs as well. So we do work with a lot of commercial space companies, a lot of academia research that we do. So we get really that broad spectrum across the entire industry, engaging with a lot of different folks in the industry.
And so NASA is a huge organization. And so how does kind of what you guys do at Marshall sync up with some of the other kind of locations around the country?
Sure. So Marshall, one of our primary responsibilities is the propulsion side, and we're also engaged in the vehicle side. So for the SLS launch system, space launch system, Marshall works the core stage engines, the RS-25 engines. We also work the boosters on that, and we're also involved in the tank and a lot of the integration and the program side of that, where a lot of our sister centers are engaged in the crew capsules for the astronauts and different avionics and different aspects of that. So we work closely with all the different centers, including a lot of the research centers and JPL and Ames and Langley, and have a lot of different projects outside of even some of the commercial space flight, where we do a lot of technology development, and each of the centers have different core capabilities, a lot of different expertise at the center. So it's fun to be able to work across these multidisciplinary integrated teams across the organization.
And part of that kind of exploration, innovation is additive manufacturing. So maybe just start at kind of the 30,000 foot views, like what's kind of the main use, or kind of where did the use of additive manufacturing get started with some of the work that you guys are doing there?
Sure. Yeah, certainly it's an exciting field as your whole podcast is involved with. We started additive manufacturing with propulsion in about 2010. Prior to that, we had worked with a lot of 3D printing, I guess is really what we were calling it at the time, and plastics in terms of prototypes and tooling, stuff like that. And we were engaged with some of the first metal additive manufacturing on the electron beam powder bed fusion in the early 2000s at Marshall. And I remember I still have some of those initial parts. They weren't the prettiest looking parts and had a lot of porosity in them, but I think we saw the vision for it, but the technology just wasn't quite there yet. And then as laser powder bed fusion started to come online, and around that 2010 timeframe, there was a few vendors that were out there as we started to see where this was going, and really the opportunity to infuse it into some of our work. And some of my colleagues at Marshall were involved in a test program under the J2X upper stage engine. This is part of our Aries program. And they did a additively manufactured of an Inconel duct. It was a 180-degree bent duct. So it looked like a very simple part, but the tooling and the traditional fabrication of it was very complex. It was very long lead time. So they started with the development of that and went through all the mechanical properties and inspection of that. And then ultimately we got to hot fire test that at Marshall. So it was pretty exciting to see that exposed to some of the environments and in some of our rocket engine components. And I think after that, that convinced us to, okay, let's take the next step with this. It's a simple duct, but we saw a substantial cost savings and schedule savings on that alone. So the next steps were Marshall had purchased some machines so we could do our own internal development. We started looking at other components. And the area that I'm specifically involved in the group that I work in, so I said we're functional components, and specifically combustion devices and turbo machinery. And I work on the combustion devices side, which is injectors, chambers, nozzles, ignition systems. And those are very complex components, traditionally manufactured, have a lot of piece parts, a lot of joining, different materials, and of course, very harsh environments in which they operate. And specifically, the components that I've been more interested in have been the combustion chambers and nozzles, where you have these series of integral channels that we have to actively cool the walls. And after seeing some of that early additive manufacturing of the duct, we saw the potential of, we have these very complex components with all these internal features. Here's an opportunity for additive manufacturing to go make these components and simplify that overall fabrication cycle. So I think the vision has always been there, but again, the technology, the supply chain, the materials, a lot of that has had to catch up. And that's what we're trying to do now. We have a lot of development activities to bring us, to where we are today with that.
And I imagine too, given how long that you've been at that process, you have these different factors of there's probably design elements that you want to change, geometries and to improve performance. But then you also have these new processes, new forms of material. Maybe they're the same base material, but you're putting it together in a different way, and then different post-processing and just process control. Can you talk a little bit about that's a big elephant to try and eat as you go and try and make new parts, especially for very sophisticated processes and rockets and propulsion that you're doing. Can you talk a little bit about how that process has evolved over the years that you've been doing additive at Marshall?
Right. So I think, additive manufacturing has definitely gained in popularity, which is great because you see a lot of these new companies out there that are doing it, and a lot more on the supply chain side as well, from the powder through the service companies, through the post-processing. But we're all learning as an industry on that. And from our perspective, it's another manufacturing technology, and we need to proceed with caution. Even though it's exciting and you want to jump in and start designing and testing parts and implement them in flight, our first responsibility and duty is to make sure that we're doing it safely for our crews and their families and all the people involved in that. So NASA is heavily involved in certification and coming up with that framework for how do we do this safely? How do we understand the process sensitivities? What are the different tests that we have to go do. How do we certify a machine? How do we certify an operator? Certifying the powder side of that, and then all the traceability of that. So having that rigor is probably the first fundamental step in this. And again, we've learned over time with that. One of the challenges with it is we can go lay out a certification program for, let's say, laser powder bed fusion, but then you change a material or you change a process, and now you need to start over with that, because it's going to be different for every process and every material. Now, the framework should be similar with that, but again, we want to have that detailed rigor on this and make sure we do it safely. When you mentioned the supply chain side of it too, like the post-process and everything, that is something that I think a lot of people tend to omit or don't put enough time into. The culture and the paradigm of design and manufacturing has changed a little bit with additive manufacturing. Is previously you would design a part, you take it over to your manufacturing engineer, your machinist, and say, hey, can you make this? And they give you feedback on it, and you may go through some redesigns with that to make sure that it was manufacturable. Now, some of that still exists with additive manufacturing, but your design engineer is almost your manufacturing engineer right now. Is I make this CAD model, I supply it to my vendor or to my additive manufacturing engineer, and they go print it. So I think the first thing, with that supply chain too, is making sure that we have really good training of our design engineers. Is they need to understand that entire process. What are all the different rules of thumb that go into designing a part using any one of these processes, whether it be laser powder bed fusion or direct energy deposition or some of the solid state metal AM techniques that are out there. So having that set of design rules, then they need to understand it from a materials perspective too. We're not saying that our design engineers need to be materials engineers, but they need to understand that the properties are going to vary from process to process. So what are the requirements that I need? Am I going to meet those basic properties of it? And an example is like directed energy deposition. I might be able to build a part really, really fast, but I might have some enlarged grains as part of that. I'm going to get a variation in my properties. So understanding that not all metal AM is the same, I think is really a responsibility of all of us and our designers. So they need to understand the materials aspect, but then the post-processing aspect is really important. Again, I can go make a model and I can go build it, but oftentimes the success of a part in an application is going to rely on that post-processing. Can I get the powder out? Can I confirm that I've gotten all the powder out of it? What are the heat treatments that I perform on that part to make sure that I'm getting the optimal properties of that? What interfaces do I have to machine, or which ones do I have to polish? Can I access the areas that I want to polish? So all of that really rolls up and I think goes back to the fundamental design portion of it. If I don't design for it early, and if I'm not aware of all these downstream steps, then the part may not meet the requirements, or I might see some performance impacts when I put it into service.
For sure. And I think the also neat thing about what you guys are doing, kind of being on the cutting edge and going through all of this rigor, is you do put a lot of information out, either through conferences or discussions like this one. And I've really kind of liked the standard 3716, like that was that you guys put out for kind of really going step by step, detail by detail. And if you're ever interested in kind of digging into the details of how you might qualify an approach to qualifying a part, like I think that step by step process that you just outlined, and thinking about all the different kind of islands of information that's coming in and steps in the process, it's really insightful for applying it to any industry that's coming up, not just aerospace, but helping medical, or think about it in medical terms or other industries.
Right, and I think that's one of the advantages on the government side is we're funded by the taxpayers, so we are able to provide this information, to industry, and that's one of our roles too. Where if it's NASA funded, we can share this data. It's non-proprietary, and we do want to see industry take that and run with it. So these lessons learned. For us, are important to provide in conference papers and journal articles and the different specifications, because I think there needs to be an independent organization like the government as well, and not necessarily a company that helps develop those standards and can work across a lot of different industry partners and gather their inputs on that. So I think we do have a unique role in this. As a matter of fact, along those lines, we are in the probably about halfway through writing a book on metal additive manufacturing. This would be published under AIAA, nonprofit, and the objective is to put more or less what I described earlier in there and put a lot more context to it. Is from a design engineer's perspective, what do they need to know? How do you do the process selection? Why would I select powder bed fusion over DED, or DED over cold spray, or cold spray over ultrasonic, or ultrasonic over, there's so many of them out there, and just trying to unwrap and simplify some of that, because we get these questions pretty regularly. What are the processes that I can use? How do I design for it? What's the post-processing that I do? And I think we're so ingrained in this now, and a lot of us that have been doing this, that sometimes you don't think about those fundamental steps, and it's good to write that down and get it out there. And I've found that in writing a lot of this down and putting it into a book that somebody else can make use of, you certainly learn a lot more about it as well. And we've identified a few gaps that we need to go investigate and make sure that we have data that supports that. So again, I think that's one of our roles. We're excited about that. There's a lot of people from industry involved in that, both academia, industry. We probably have 40 or 50 contributing authors to this. And again, it's to put together that volume of the practical side of additive manufacturing for propulsion application, providing examples. We have basically the end-to-end steps in there that we described earlier, from the process to the post-processing, the materials, the feedstock, the powder and the wire side of it, and then the certification of that as well. So again, one of the roles that the government helps play in some of this, like you said, to get that information out there and publish when we can.
And along those lines, I mean, you've described so many kind of different steps of the process. How do you and kind of the organization think about kind of training / hiring, or kind of building the team that's working in kind of relation to kind of these additive processes? Is it more focused on kind of, we need someone has expertise in propulsion and then we can teach them the additive stuff? Or is it kind of the other way around, where we need someone that knows additive and can apply it in different contexts? Is there kind of a strategy that you've seen over the last number of years that has kind of taken hold in terms of kind of training or kind of building the organization out around or related to additive manufacturing?
Right. I don't think there's necessarily one skill set or discipline that we're looking for, because with additive manufacturing, you have so many different disciplines engaged in this. I think the first thing is people's excitement about the technology, is in wanting to push things forward, and interest in developing new aspects of it, or digging into some details that maybe some gaps that we haven't understood before. And I think that's part of a lot of writing this down in the book, is so that we can hand this to some of our new engineers and say, okay, here's what we've learned, but please go add to this. And like I said, a lot of it is culturally based too, is we've learned that it's not as serial as maybe a design process was before, that we may have to start with some limitations of the process and find out that We have to, the size limitations of large parts or the size limitations of some of the smaller machines. What is the supply chain that's out there on that, and bringing those lessons early to the team on that. But again, there's different aspects from like materials engineers, right? We have materials engineers that are coming up to speed on additive, and there's different ways that we've had to look at materials in terms of, well, now we look at the melt pool and the structure of that, and then you can go through all your heat treat developments. So I don't know if there's a particular skill set. I think you have to have all the skill sets involved in it. We have other research engineers that are really great at parameter development, and that's a different skill set than what a design engineer is going to have. Or my role as a component engineer, we're involved in all the different disciplines and trying to link together some of those disciplines. For instance, for like if I'm leading the structures team on the design, and the first question is, well, what are the properties, of additive parts? And I think we don't have all the properties of these for designing for a new part. We have to go test those. So, we have to start with something. So we might take a knockdown of some initial raw properties until we get the data that goes into that. So some of it we're I don't want to say we're learning on the fly, but we're learning a lot of lessons as we go along, and just try to capture those, and like I said, put it into documentation. I think just trying to give some of our new folks an opportunity to dig in too, and take on a smaller task, and it might be something like, okay, how do we do powder removal? Well, here's how we've always done it, and have some of these new folks come in and say, well, have you thought about doing flash chemical milling, or, some of this post-processing techniques? Well, yeah, maybe we've thought about that. We haven't thought about it, but go develop a project and go do that, because that's all important data to go collect on this. And I think there's all these detailed areas that still have a lot of research to be done. And of course, we work very closely with academia partners too, on both the materials characterization side of things. But we're also trying to train academia on, there might be some of the fundamental characterization, but then there's different ways that we do things in industry as well. I think one of the examples that we have found lately is when we're doing mechanical properties. It's easy to do small samples in a lab furnace and quench them really quickly, do a water quench on it. But if you look at like the industrial side of things, we're using these large furnaces. You're usually using an argon quench on things. So we're trying to also make sure that academia and industry is aligned in some areas for how we have an understanding of additive manufacturing. Because there's another example like that too, where a lot of times you see some of the literature that's out there, and they may not do a stress relief on it, where we often do stress reliefs on it. So it's all those details. I know that I got into a lot of, probably a little bit deeper in some areas, but making sure that we pull all those details together and somehow capture them, and then try to train our new engineers, no matter what discipline they are, some of that overall process.
So this may be a dumb question, but when is kind of the idea for a lot of the parts that you're producing and kind of getting the qualification for, is kind of NASA, Marshall going to be the prime manufacturer for those that go on the vehicles? Or then do you also partner with outside organizations to help kind of with supply, or kind of building up quantities that you've determined a pre-designed kind of, here's the path and here's what we're expecting? Right.
No, that's a great question. And we don't produce anything. We do the early development. We have machines, at our disposal inside to do development on, but we don't produce anything. We don't compete with industry on that. Is we want to help enable industry. So a lot of our goals are to help set up the supply chain for this as well. And that might be new materials, processes that need to be advanced. Um, so from like the powder supply chain, an example of that is NASA has been heavily involved in trying to develop some of the new copper alloys for combustion chambers. We need a high conductivity, high temperature material that's going to survive in our chambers. And early phases of additive manufacturing, the Inconels were well developed, and then some other materials came along. And for a while, we didn't have capabilities for copper, so we took on the role of let's go develop the copper, the GR-COP materials, which are a copper chrome niobium alloy developed for combustion chambers. Was developed at NASA Glenn Research Center back in the 80s, and we did that initial development, worked with some of the powder suppliers on that. And since that early development in 2015 or so, we've seen it grow a lot. So there's a lot of suppliers out there now of the GR-COP. There's several powder vendors for the GR-COP. And I think that is just shows what we're trying to do with the infusion of this, is we want to see industry take that and run with it, because ultimately we can go purchase the parts for our missions from these commercial suppliers. And then beyond that, other government organizations and commercial industry can purchase those parts as well. So we don't make anything, that we're supplying. That's all done through our prime contractors and our vendors. But one of our roles is to help do that early development, to infuse that and enable that. And we're continuing to expand that. New materials. There's another hydrogen resistant material we're trying to develop and infuse that out to industry. And then even some of the processes too, as NASA has a lot of great research opportunities, like our SBIR program, where you can go in and do early stage development and show feasibility of a concept, and then possibly go to like a phase 2 SBIR where you can really dig in, really develop that. And we want to see those type of successes, because if we can have a supply chain set up and we can be buying parts cheaper, and commercial industry can be buying parts cheaper, that we can be flying more regularly, and I think all of us benefit from that. So that's another government role that I do see, is helping to enable and supporting industry.
And I imagine too, you've kind of, since you do a lot of that, or all the development work, you also have an idea in mind of what the qualification of any supplier of parts back to NASA or the government would be like, right? And that is, from my experience in talking to some of the small manufacturers and medium manufacturers around the US, is like, that's something they're wrestling with, is, okay, we see the writing on the wall that additive manufacturing is becoming more more commonplace. It's a big investment from a capital equipment, but also then the practices, the know-how, the standards, it's getting more black and white, but it's still probably more gray than black. And so I imagine kind of helping fill that role too, and working closely with someone that's actually done it is helpful.
Right, and it's not easy. It takes practice. I think somebody that's coming new in additive manufacturing, you see all the success stories. You don't see necessarily all the failures with it. So you think, oh, cool, I'm going to go design my part. I'm going to send it to this vendor. It's going to come back and it's going to meet all my geometry that I needed and all my surface finishes, and it's going to perform beautifully. And then you get that phone call from the vendor saying, hey, we failed the build because I had a recoder arm crash into the part, and I have to rebuild it. And that's one example. There's 1,000 things out there that can go wrong with it. A lot of the time it can be just the design, because we have a bad design and we need to go try the print of it to see if it's going to work. So it takes iterations to go do that. It takes practice to understand, yes, I do need to do a stress relief, and I do need to perform these other heat treatments, and I need to design ports in there to get powder out of it. And it's going to take time for industry to understand that. We see new vendors that have set up operations, and they don't have that tribal knowledge and that experience. So, and again, that's, I think one of our roles is to help train in some of those areas, at least provide some of the documentation of here's what you should do, and realizing that our certification, our standards, there's a lot of steps in there and a lot of involvement, but a lot of those steps have come out of failures that we've seen, or lessons learned even from traditional manufacturing. And I think one thing that I've said before, which surprises some people, is don't use additive manufacturing unless you have to, unless you see significant advantages of it. It doesn't fit every design case. If you can go machine a part and make that work, it's probably going to be cheaper to do that. So by no means are we saying that additive manufacturing is going to replace every manufacturing process out there. It's another tool in our toolbox, and we've seen huge advantages from it in both the cost and the schedule side of it and performance side of it, but use it when it makes sense. So in our applications, we're using a lot of materials that are very difficult to machine traditionally, have a lot of internal features, a lot of complexity to them. So that's where we see that additive manufacturing has advantages for us, but there's still a lot of parts that we machine on that. And I think that's another responsibility of the design engineer, is to understand how to trade for that. And don't just jump into it because it's the cool new terminology that's out there. Let's do it wisely and make sure that, yes, it's going to provide us a cost advantage and we can do it safely. So understanding that trade of it too, more the programmatics side of it is I think very important as well.
Absolutely. And kind of as we wind down kind of the podcast, for kind of people that are exploring additive manufacturing, may kind of be in school or thinking about kind of shifts in some of their careers, do you have kind of a piece of advice that you would kind of offer them? I think having all the cool NASA videos and even the Mars rover that has some additive manufactured parts in it, like there's so many inspiring stories that you guys can tell about these big visions, but are there kind of practical things that you've learned over your career that could be helpful in kind of the next generation of people that might use the technology or think about careers in the space?
Sure. I think a few words of advice there, stay curious. There are so many areas in additive manufacturing that have yet to be researched, new materials and different processes. So it's easy to find a niche in that and dig into that. And I think also taking on some of those difficult roles, that there's areas that people may not want to research that because getting the funding and putting together the plan that goes with that, there's a lot of effort involved in that, whether you're in academia or at a company. But I think some of those early developments and curiosity of that is going to help continue to push additive manufacturing forward, challenge some of the part designs. Of course, we want to do that safely, but there's new things I think we can explore there with that. So finding those opportunities, and sometimes they're not always obvious where you find them. I mentioned before that post-processing I think is really important. I think there's a lot of areas of post-processing that we have yet to understand and evolve. So I think there's a lot of opportunities for newer engineers to research those areas, and academia engagement in that. And it's exciting to see because there's more and more users of it. And I think it's definitely a common term now. 3D printing is not just a technical term or an engineer term anymore, that most people know what that means, but really understanding the process of it, all the detailed steps of it are my other words of advice on that. So don't just dive in without knowing the detailed steps that you have to do to make a part successful.
Awesome. And I'm sure there's a lot of stuff you can't talk about, but is there anything on the horizon in 2021 that you're excited to
see come out of NASA, out of the Marshall Center there?
Yeah, so I think we're developing a lot of new materials and trying, again, to infuse those in industry. We're working some new processes. So we've been heavily engaged with the directed energy deposition process going very large scale. So now we're doing parts with integral features that are 1.5 meters by 2 meters tall. And a few years ago, that was just unheard of for us. So that's something that I'm definitely excited about, is seeing the scale grow. And then when I mentioned materials, one of the aspects of it is we've been using a lot of these, I'll call them traditional AM materials, the early materials that were developed, but they're not necessarily the best materials for our applications. So these hydrogen environments and highly dynamic and high heat flux environments. So a lot of these new materials are geared towards rocket engine type applications. So now we're making materials that we need for our applications, not just materials that are available. So those are a couple areas that I'm excited about. And, certainly there's a lot of new technologies that are out there, and a lot of the design topology optimization and stuff. So I think over the next few years, it's really going to be exciting to see all of this stuff start to come together.
For sure. Well, Paul, thank you so much for joining the show today. Really appreciate it. This is great stuff. Thank you so much.
Absolutely. Thank you.